I'm going to finish up this series of videos covering regression pitfalls by looking at overfitting, extrapolation, and missing data. So starting with overfitting, this is if an overly complicated model tries to account for every possible pattern in sample data but generalizes poorly to the underlying population. And so what this means is we are getting over-complicated models that really aren't supported by the data. So it's important to always apply a sanity check to make sure that any model that we come up with does make sense from the subject matter perspective and that the conclusions are actually supported by data. So to illustrate this, let's actually go to R to have a look at this. So we've got some data here, and if I draw a graph of it, so let me zoom in, we would probably say, okay, there's a fairly strong positive linear association between x and y. I think a simple linear regression model here is just fine. So I can add that. But we've been learning about the possibility of polynomial models where we can add higher and higher powers of x to the model. And if we do that, we can get a very different picture of what's going on. So let me redraw the graph. But this time, I'm going to add a model that's got x squared, x cubed, x to the 4, and x to the 5 in it. And that's sufficiently complicated of a model that the regression line can go through the points exactly with no error. And so you might go, well, that's fantastic. I've got a model with no error. But if we just apply a sanity check to this, we've measured these data points and we are modeling a relationship between x and y. We've only got these 6 data points. Does it really seem likely that the model that relates x and y is represented by this crazy curved line going through all the points? For example, if we have a value of x at, say, minus 0.6, actually let's go back and just draw the plot without that crazy line going through it. If we have another point that we've measured at x equal minus 0.6, somewhere in this area, where's it going to be? Well, it's probably going to follow this trend somewhat, so it's, I don't know, maybe going to be here somewhere at about maybe 3.5, somewhere around there. But of course there's going to be some error in it. Does it seem likely that the point is going to be kind of up here and lie exactly on this crazy overfit, overcomplicated 5th degree polynomial? Well, unlikely. This is a very clear case of overfitting, and if we try to generalize this to the population, we're probably not going to do very well. A far better model in this case is this one. It's tracking the overall trend in the data, but it's not getting hung up on trying to get the error down to 0. So that's overfitting. So this example here that I've just worked through, this is just to kind of illustrate the problem. Where this comes into play in practice, though, is in models with many predictors, and the problem that can occur is that we can try and add all these extra predictors or transformations or what have you to try and get our model as perfect as possible, but it's not actually modeling the underlying pattern in the data. It's just over modeling all the twists and turns in the sample data, and it's not really representing the population relationships very well. Okay, so that's overfitting. Let's move on to extrapolation. So extrapolation, this is when we're using our model results to estimate or predict a response value for an observation or a group of observations with predictor values that are very different from those in the sample. And so what we're trying to do here is we're trying to use the model for a purpose that it wasn't really designed for. And we're trying to make a prediction well outside the scope of the model. And that's dangerous because we've actually got no data there to support our conclusions. So I'm going to illustrate this with some data. And I'm going to fit a couple of models, and then let's take a look at the data. Okay, and let me blow this up again. Where's my plot? There it is. Okay, so let's just focus on this part of the plot so far. I've extended the axes because I'm going to illustrate what can go wrong with extrapolation, which is when we're trying to predict outside the scope of the model. And the scope of the model in here is represented by the range of the value of the predictor, which is labor hours in this case. So I've extended the axis so we can see what might happen if we extrapolate beyond the scope of the data, the scope of the model. So here we can see there's a positive association between labor and production. As labor increases, production tends to increase, so that kind of makes sense. It's not clear whether we've got a linear relationship here, or maybe there's a non-linear relationship. It almost looks as if when we increase labor down at this end of the range here, production goes up quite dramatically. But when we get up to this range of the predictor, we increase labor hours and production increases, but not by as much as it did down here. So it looks like if I trace out the trend in the data, I'm tracing out a curved line. So that's why I've got a couple of models on the go here. One is the simple linear regression model, which is going to be a straight line, and then this model is the quadratic model. That'll allow us to fit a curved line to the data. So let's put those two regression lines on there. Okay, so that's what I've done here. So we've got our simple linear regression model represented by the straight line and our quadratic regression model represented by the curved line. Okay, and just kind of looking at it, it looks like the curved line is doing a better job of fitting the data. And if we think of it from a predictive perspective, if I'm trying to predict production when labor hours is 6, so let's say I'm trying to predict this point here marked by the X. My linear regression model would give a prediction that's a little bit low, and my quadratic model would give a prediction that's a little bit high, but they're both pretty accurate. Okay, so in terms of prediction, there's not a lot of difference between these two models with respect to predicting this point here marked by the X. But what if I was to try and predict this point over here? Okay, so here I'm trying to predict production for labor hours of 12. Should I use one of these models to make that prediction? Well, it's dangerous, right? Because I don't have any data out here. And so this is what I mean by extrapolation. If I was to use either of these two models to predict this point over here, I would be extrapolating my model beyond where we have any data to support our conclusions. And that can get you into trouble. And it's quite dramatic what happens here. If I extend these regression lines, okay, so the linear regression line for the simple linear regression model, it's clear what happens there. It just keeps going up here, okay, and it's going to end up with a prediction that's way too high. But can you guess what happens to the quadratic model? I've got a bend in the curve, and that bend is going to keep going, and actually what happens is it starts to come down. So this model actually ends up with a prediction that's too low. If I can just add those two lines to my graph, you'll be able to see. Okay, so here's my simple linear regression model prediction, way too high. Here's my quadratic model prediction, way too low. So in this case, it's very dramatic that extrapolation is going to give me a bad prediction, no matter whether I use the quadratic model, which appears to fit the sample data a little better, or even if I use a simple linear regression model, it's going to give me a bad prediction. Okay, so this is an illustration of how extrapolation can cause real problems. Okay, so bottom line here is be very wary of extrapolating model results beyond the scope of the data. Let's move on to missing data. So missing data is when there's particular values in the data set that have not been recorded for particular variables and observations. So they might simply be mistakes that we're missing that data. The data might simply not be available for certain observations. But for whatever reason, we have some missing data. So let me show you what that might look like. So here's some data with y and 4 predictor variables. These NAs represent missing data. Okay, so for example, observation number 6, I've got values for y and x1 and x4, but I'm missing values for x2 and x3. Whereas observation 13, I'm only missing a value for x2, but I have values for all the other variables. Okay, so this is an example of some missing data. Let me show you how that might impact our modeling. So let me fit just a multiple linear regression model with all 4 predictors, summarize what's going on. We might look at these p-values in this column and think to ourselves, okay, looks like maybe x1 is not associated with y once we've controlled for x2, x3, and x4. So maybe I could try dropping x1 from the model and see if we get a better model. So let's do that with model 2. Summarize what's going on. Now the other 3 predictors are all significant. I've got a pretty high value of r squared. Everything looks good. But this model has only been fit to 25 observations, and in our data we had 30 observations, so we're missing 5 out of the 6. So we're missing, for example, this observation 29, because we're missing the value of x2 for that observation, and because I've got x2 in my model, I can't use that particular observation. And similarly, I'm missing observation 19 and observation 16 and observation 13 and observation 6. Okay, so I'm missing 5 observations, and this model, although it looks kind of good, it only applies to 25 out of 30 points. So that's not good. Let's contrast that with this model here, model 3. So model 3 has x1, x3, and x4. Now remember, it was x2 that had the most amount of missing data. So let's fit this model and take a look at it. Looks pretty good, just from the perspective of I've got 3 significant predictors. I've got a pretty high value of r squared. Not quite as high as this model, but it's essentially just as high, 95% rather than 96%, but yeah, it's way up there. And this model has been fit to 29 out of the 30 observations. The only one that had to be dropped because of missing data is number 6. Okay, because that was missing x3, and I've got x3 in this model. Okay, so ordinarily we might favor model 2 because it's got let's look at adjusted r squared, 0.9521, higher than 0.9472, residual standard error, let's see, 0.849, smaller than 0.8524. So from that perspective, model 2 does look better than model 3, but it applies to much less of the sample. So from that perspective, we might actually favor model 3 in this case. So this just illustrates that when you've got missing data, you've got to kind of weigh that up in your modeling and think about whether it's going to perhaps influence some of the decision making that you're using. So in this case, I think I would probably say, okay, this is the model that I prefer, because it applies to a bigger sample size, even though it's not quite as high a value of r squared or as low a value of s as this model. This model applies to a much smaller sample size. You wouldn't want to kind of go another step though and say, okay, maybe I can find a model that applies to all the data. If you want to apply a model to all the data, in this case, you'd have to drop x2 and x3 because they were the variables, the predictor variables that had some missing data, and then you're left with just x1 and x4. But then r squared goes all the way down to 0.64, and s jumps up to 2.3. So that's a terrible model. Okay, so you have to kind of weigh all these things together to determine which is going to be the best model for your particular purpose. So that concludes this series of videos on regression pitfalls, and we've just finished up by looking at overfitting, extrapolation, and missing data. And in the next series of videos, we're going to consider some more aspects of model building in the context of multiple linear regression.